Oh well, so yeah, so I am the author of Gears. I'm sure everybody has a little bit of hype hearing it since it's been mentioned a few times in the conference already. And here I'm gonna talk about an overview of the thing and yeah, a little bit about me. My name is Nguyen. It's a really hard name to pronounce. I have thought for a long time on how to pronounce it in an English-friendly way, and I came up with one. So it sounds like this. It's like we as in win, and then n as in enter, right? So you come together, it goes Nguyen. That's good. Cool. So I'm a second-year PhD student at LAMP, Martin Oderski's lab at EPFL, and I previously worked on the delimited continuation implementation in Scala Native, which if you've seen Wojciech's talk, it's been there. I've also worked on code bases in async Rust, Go, Node.js. I learned a little bit of Haskell in the industry, but currently my full-time work is on Gears, of course. And so, okay, so what is Gears? Recall a long, long time ago at Scalar 2023, in Martin's keynote talk, we mentioned a little bit about direct style future, right? So we had this suspend construct that gives you basically the power to wait for a future and do it cheaply, right? And that came with LAMP EPFL/async, an early stage prototype, or as he called it, a straw man of what's to come with futures, channels, and how to do structured concurrency. And yeah, it was a straw man, and now it's Gears, an experimental library for asynchronous programming in direct style Scala. We made 2 releases. I don't really like the 0.0 point things, so I do 0.1 and 0.2. RC1 is coming soon. It is kind of, oh my god. Oh, it's back, okay. You can hear the nervousness. So we have 2 releases. The second one is going along with Scala Native 0.5 right now. And of course, because it goes with Scala Native, it works both with Loom and Scala Native. And we have actually prepared fairly good documentation that I'm pretty proud of. You can see it on the website. I'm going to post a QR code at the end of the presentation. Okay, so what are the primary concepts, right? So as mentioned before, we, since Loom, Looms gives you virtual threads that basically lets you do blocking operations cheaply by taking the thread itself and suspending it, throwing it into a queue away from the physical thread and letting other virtual threads do the same, do their own work, right? So that, and on Scala Native, we have delimited continuations, and you pair that with a scheduler, it gives you basically the same thing. And notice that it requires you to be part of it, right? So inside Loom, you gotta be inside a virtual thread. Inside Scala Native, you gotta be under boundary suspend in terms of delimited continuation. But being Scala programmers, we can, of course, model the thing as a capability or a context, and here, an async context. And that's one of the core concepts of Gears. That is async context, the capability that allows cheap suspension of computations to wait for future events. In short terms, it gives you .await. And comes with it the rest. We have futures, which is a very straightforward creation of concurrent computations. You sort of start a future, it goes running in the background. We have some concepts of structured concurrency, and we're going to have a little bit into the sources and channels, which is a tool, some tools in a toolbox that Gears give you to deal with the complexity of external and interdependent concurrency that happens between futures and with the outside world. Okay, so let's just drop into a simple example. Right? Here we have sort of like a weird function that takes 2 files and read them and pass them into numbers and add them. Right? Something you would do every day, of course. So here we have the function itself taking two files, you can notice there's an async context, which we will refer to this as using async all the time. It starts a computation group where you start the computation of reading F1 inside a future while just doing it straight up for the second file. And at the end, you'll wait for the first future, and you parse it into an integer, and you add it with the second thing. Like the second thing is basically a string. And you can see that here, that V1 and V2 runs actually concurrently, because V1 runs in the background, and V2 runs in the foreground. And await actually takes the async context and suspend it until the future, the background computation is ready, and it returns a string. And of course, like the API itself is using async all the way down. So once you have a file, the read method is going to be read using async returning string. And if you look at the async context, it can be viewed as both a capability and a context. So as a capability, it allows the function or the computation to be suspended, right? So you give it as an async context, it has the suspend method. It signals the possibility of cancellation. So if you have an async context, you are running in a virtual thread, you're running in delimited continuations, you can be canceled, you can be interrupted. It is some sort of a side effect tracking, right? Because you have the side effect of suspending, and it gives you a little bit of safety, right? Doing blocking operations under an async context is something that should be cheap to do. And as a context, it also gives you some runtime information on how to perform suspension. So how here is a little bit of an asterisk, because under Loom, it is very easy to assume that, well, Loom does everything for you. On native, it's not that simple. And once we go into WebAssembly, it's going to be more complicated as well. And also, it provides you sort of an attached scheduler, so some interface similar to the execution context. And finally, a structure scope, which we will mention later. But more importantly, here we just model the async context as an implicit parameter, right? So all of your functions, like if you think about it as like suspend functions or async functions coming from other languages, here it is a little bit similar, but not really. We just have it as an implicit parameter. You pass it as a parameter. You deal with it almost as a value. And no promise, no future, no monads needed. Everything is just straight up direct style. The API itself is almost a blocking API, right? So you have two functions, f and g, using an async context. You call them in sequence. Here in the function h, it just blocks until f returns, and then it blocks until g returns. Blocking here means suspending, of course. And yeah, it looks exactly the same as if you don't have the using async at all. OK, so sequential actions, right? So the kind of things you do with, for example, in CATSFX, you have a list, and then you do flat map on it. Those are actually sequential, right? You await for each I/O in a sequence. Here, we have sort of the same thing. I should remember not to touch the cable. I'm so afraid the clock's still running. OK. OK, so we have an item where we have a transform function, which changes to something else, and we have an invalid method that returns a Boolean while returning whether the item is valid or not, right? Both are using async, so they are suspending functions. But here, if we have the transform all function, taking a sequence of item, you can just do filter and map on it. Those are the actual sequence filter, sequence map methods that are defined in the standard library. And here it is noticed that capturing the async context is completely fine as long as they don't persist, right? So under an async context, if you invoke the async suspension mechanism, is completely fine. OK, so with all the suspending stuff, what we're here is actually for concurrency, right? You want to spawn things that run at the same time. And so Gears actually give you a very simple method of doing that by spawning futures. Right? What you do here is just call the future apply method right here. Oh, wait, this is a lot of things. Looks very complicated. Never mind, no, it's not. Uh, Here's the exact same thing, right? I'm just hiding all the implicit parameters. In real life, you're writing a lot of these kinds of code. So here, what we are doing is just spawning two futures running f and g in concurrent. And the third thing is a future that sleeps for 1,000 years. Of course, it's going to take that long to finish f and g. So what we're doing here is we try to run f and g in concurrent and await for their results and then add them, right? We don't really wait for the third future, and therefore once v1 and v2 are completed, v3 is automatically canceled. And what that means is that once you return from spawn, there are no more futures running. And that is sort of like an important element of structured concurrency, what is like sort of what to come. And the async context itself also introduces async scopes. So futures are probably scoped to their context. So here we have async.group. Async.group is something that gives you a group, an async scope based on a parent scope, and it manages all the futures that are spawned under it. And so once you return from this group, let's say at this point, both A and B are canceled and cleaned up. And here as well, if we call a method f passing the async context, once f returns, no futures under f remains. So we completely cleaned up all the futures that f creates. And that gives us sort of like a structure in the structured concurrency. It is sort of like a concept that is used in different languages with a little bit different meaning. But in here, it basically means that your async contexts always form a tree. And as always, like because you're programming in direct style, you suspend and wait for things. And so with or without the async context, all your function calls will act sort of the same, right? It will block until it returns. And that means there are no dangling futures, nothing running in the background out of your control if you stick to spawning futures and doing async. Okay, so once we have futures, we might think about composition of futures, right? So the first thing you can do with a future is, of course, await. So what await does is that it returns the result of the future, and if the future throws anything in between, it rethrows the exception. And if you want to quickly catch the exception, there's .await result that returns a try t. T is the type of the future, by the way. Okay, second thing is OR and zip, which are like very simple future composing methods that basically, well, OR gives you a future that completes if one of the two completes, and zip gives you a future that completes when both of them completes, right? And so you can see here, v1, v2 is a tuple. When you take three futures, 1, 2, and 3, you erase the latter two, and you zip it with the first one. You do await, and you get two values back. Especially for a sequence of future, though, there are some extension methods that make working with OR and zip way easier, and you don't have to fold everything, where we have await all, which is basically you do a dot map and then await on every future in sequence, but with a caveat that if any of the futures throw an exception, it will throw immediately instead of waiting until it's turn to throw. Await first is sort of like raising all the futures and returning the first one to succeed, ignoring exceptions, of course. Unless all of them throw, then you get everything back. Of course, and the final thing is both await all and await first have a with cancel variant, which basically means that if the thing returns early, right? So if a wait all encounters an exception, or a wait first encounters a succeeding future, you cancel everything else. And okay, so the next thing is async.select. So we kind of stole this feature from Go. So in Go, select is a thing where you can give multiple channels to wait on, and it would sort of raise and give you back the first thing that succeeds and lets you work on it as if it was like a match expression. Here we have sort of the same thing as well. So we have two futures. You can put them into a select and with a handle method. So a handle method takes a value out of that future when it arrives, and it runs the body, right? Async.select would block until the race completes, and therefore all your handler methods can all use suspension, so it can capture async, but also it can deal with side effects as well, because select, just as in Go, would guarantee that exactly one of the branches will be run. Okay, the next thing I want to introduce is channels. So we sort of have this method of spawning computations, right? But sometimes you do want to communicate between those those concurrent computations. And the easiest way to do that is by another feature stolen from Go. So there's a concept called channels, which are basically a synchronization between two things where one reads a thing and the other one sends it, right? So in the most simple case where we have the sync channel right here, every send will block until somebody reads it. And the second case where you have a buffer under it, then all the sends go in through the buffer, the reads try the buffer first, and if the buffer is full, it blocks. And channels in Gears have a very simple API, like you have read that blocks and send that blocks. Simple. It can combine with the power of async select if needed. So here we have, do you see my cursor, by the way? Okay. So we have two cases where you try to send into the input channel a work piece, and you have the handle as well. You can attach a handler into it. And the other case where you read from the output channel and you print out the work result. So only one of those things will succeed, and one of the handler would run, and the other one will not happen. So you can guarantee that all your work will be done sequentially as inside a select. And channels will come in 3 variants. Well, we already introduced the sync and buffer. There's also another variant of unbounded channels where the buffer is unlimited, basically, and all your sends will always succeed immediately. Okay, with all of that done, there is another concept where, well, of course, if we just stick to structured concurrency, all is fine, but at some point you have to deal with external events, right? And they are inherently unstructured because they don't come from your structured program. And so we have a common abstraction for all things that you can suspend to wait on, or called async sources, async source, and it comes in several variants. We have already seen the future that you spawn. That is something that you can, that is an async source, but also channels are an async source. And here we also have a promise, which is actually very close to a Scala promise right now, where you can sort of create it and complete it manually, but also there's a future with resolver that helps you with dealing with converting from callback code to using futures, right? It is a little bit like io.async, where you have future with resolver. It takes a resolver, you can call complete on it, so you throw that as a callback, and it returns you a future that completes when the callback is run. The more generic source is actually some sort of stream of values where you can subscribe to get the next thing. And here we have one such source that is a timer that ticks, right? So every 500 milliseconds, it will tick. So when you start the timer concurrently, of course, under a future, you can await on it in a loop. And here we print high after every await, so the high will be run every 500 milliseconds. And of course, .await and async.select work on all sources as well, so all the things we have introduced all work. And finally, there are some extension methods that you can convert easily back and forth between the standard library futures and the gears futures. You just do as Scala or as gears. You can see here I'm converting them back and forth. Okay, so how do you actually write gears code? There are some patterns that I think during the development of gears that I found out. The first thing is error handling, right? So there are a lot of error handling mechanism in Scala right now. Like you have try, you have either, results is coming out soon, and we don't really want to commit to anything except try because, well, you have futures, right? And they might throw exceptions, and it's better to just wrap it inside a try. Oh, I talked what I was meant to talk already. Okay. We have futures wrap exceptions in a try. It's unwrapped by default. You can do await result, as we already know. Cancellation itself is handled through catching a cancellation exceptions. So they are introduced basically at any point where you can suspend. Here, you can spawn a futures that does very important stuff for 10 minutes. And if the thing gets canceled, you get a cancellation exception back immediately when you call future.cancel. But of course, you can build your own error handling, right? If you have direct style Scala, most of the time building it is very trivial. You can use a new control, which is, I think it's almost out now. You can use results with the dot question mark, like I'm using right here, or just do anything that deals with boundary break, and it will look very nice. Here we have a future of result where, hey, I want a future, I just do future. I want a result, just do result. This whole thing is failable. It's an async function, so you just call it, passing the async implicitly, and you unwrap the result with a question mark. Okay, so gears also give you a little bit of supervision. Of course, the first thing you might think about when you have cancellation is, can I run something with a timeout? And yeah, that's simple. You do with timeout, you give it a body. This whole thing takes and using async right here, by the way. And of course, using async means this body returns will block until the thing is done, or when it times out and gives you a timeout exception. The second thing is retry. Retry is sort of like a construct that builds up a policy of handling errors and trying to redo them with a delay, a backoff. Here we have retry until success with maximum failure and with a delay that is dependent on an exponential backoff with a maximum starting and some jitter. The whole thing is basically a policy that implements the retry trait that just gives you an apply method that takes an async and a block and runs the whole thing blocking until it's over. You can see that everything is basically a blocking API. Yeah, and with those two, it's kind of easy to build up an actor pattern from gears. Just do the retry policy, under a future, you have a worker. Okay, so with that async context, you might wonder, so how do I create one in the first place? Right, you gotta create it somewhere to pass it down. And if you look at the components of the async context, we want a suspension mechanism. So that is in Gears as something called suspend support. It's a delimited continuations API. You want the capability to resume a computation, right? So usually it's something that the scheduler would do. Scheduler usually sticks with I/O as well. So if you do I/O, the completion of it will be handled by the scheduler. Think ePOL or IOU ring. Of course, there's also management of child scopes, which in Gears is something called a completion group, but this is created automatically, and therefore you have something that creates an async context out of nothing, which is called blocking right now, but I think we are going to have a better name. So yeah, blocking just gives you, just takes an async block and takes all the ingredients, and it runs the thing, blocking, until you get the result back. The default implementation of suspend support are already provided with Gears async default given, but being all generic on all these implementations, it means you can have custom implementations of all of these. So you can have a custom scheduler that does your own I/O and your own continuation implementation if needed. This is especially very important for Scala native. And of course, like it lets you suspend to wait for futures, and saying blocking means like it blocks the thread. This is mostly used as part of your main method. So you use the main method that would block, but then everything else is run under futures and everything. Or it is very useful if you're doing a conversion of your code base from a blocking code to something that uses Gears, or you can partially have things running with Gears, while at the points that are bridges, you can use async blocking. And this is kind of like the current support for Gears, right? If your project imports Gears, it runs on the JVM under Loom virtual thread and scheduler. Right now, it's not really customizable. Loom doesn't give you an option to have your own thread pool. But under Scala Native, it runs under Scala Native runtime continuations, which is the delimited continuations implementation. And right now, we provide the default of the standard work stealing scheduler with ePOL enabled. But all these components are completely pluggable with Gears. Like you can just provide it as part of your main method or the entry of your project. Of course, other things are coming soon. As you can see, with Scala Native, we are looking at single-threaded schedulers, so you can run Gears under libuv, and that works just fine. You can do a work-stealing scheduler that interacts with IOU ring if you want to do really fast I/O. And in the future, when Scala.js goes WebAssembly, WASM-GC has a continuation feature as well, so we can also depend on that and run it under libuv or their implementation of a scheduler. Okay, so that's the current part of Gears. So what's coming next? Let me summarize. First, Gears gives you sort of like a new view of concurrency. Looms and continuations allow a direct style .await API, making natural asynchronous code possible. Viewing async as a capability let us use Scala's unique implicit parameter for a lean approach to managing concurrent code. And Gears basically gives you both of these and introduce structured concurrency to write your program and a toolbox as well to deal with things that are not structured. And then the next step for Gears, well, Gears itself is just a base framework, right? It gives you some concurrency. It's like CATS effects without all the ecosystems of CATS effects. And so what's coming next is going to be something that you want to suspend on, right? Most of the things you're going to suspend on are going to be I/O, so that's the next thing that's coming soon. Gears I/O is a sort of a cross-platform interface for I/O operations. Think FS2, but on Gears. So yeah, one of the things that you can see that we have a reader trait that reads a buffer and just using async and returns an int, the number of bytes read. And oh my God, I'm almost out of time. This is coming soon, and we are releasing an HTTP client that is fully using Gears interface now, so you can have a taste of how everything works out. And of course, like we know that right now there's a very simple model of cancellation, and so there will be more work on customizing cancellation models, how do you deal with things that throw, and how to supervise future better. And that's it. Thank you so much. To learn more about Gears, there is the homepage for Gears, which you can see from the QR code. Inside that, there's a book, well, a book in the sense of a Rust book called Concurrency with Gears. It's a half tutorial, half documentation style introduction to Gears that I spend a lot of time writing, so please read. But yeah, please follow its development. It's on lamepfl/gears on GitHub. You can follow me on GitHub or follow me on Mastodon. I share a lot of anime pictures, so if that's your thing, yeah, and there's a lot of documents, development documented on the Gears website as well, a lot of reports coming from our students. And of course, you can also learn about direct style Scala from last year's Martin Oliski's talk, and something that also uses direct style in Loom, that is Aux. You probably all know this, right? So thank you so much.
Thank you.